Alright, so we're moving on to the next chip, the final chip, the actual chip we'll be using in the electronics prime display. Here there's it'll be the PDSP 1883 chip, one for each of the windows here. It's an 8-digit display in green, and nice little display. They're about 60 bucks a piece. For the top display, we would be displaying our chap and our flare counts directly from the sim, and then the bottom window has the jammer mode on the left, 4 digits, and the jammer status on the right, 4 digits. And look here at the PDSP. We have the PDSP 1883, the green one. This is the data sheet. Nice looking chip here. You've got your pin 1 marked with a large white triangle, nicely marked. You basically have 4 sets of 6 pins, 2 sets on each side of the pin. They start from 1 down to, I think it's 15. And then on the other side it starts from 16 up to 30. You can see here the diagram from the side with your triangle, your pins going down to pin 15. And then over here, this is like the ass end of the chip looking forward. So pin 15 just goes straight over to 16. In other words, down to pin 15 right here. And then pin 16 will be on this corner over here, and then incrementing up. Very similar to the last chip we did, only a few differences. The digits are numbered the same way. Instead of having 4, we've got 8. They start at 0 at the left, up to 7 on the right. Should be the same ASCII table as we were working with before. And your chips, we have the reset pin, active low, very similar to the other chip. We have FL pin, active low. It's what the hash mark over top means. It means that you're sending it a 0, you're pulling it low to activate it, or you'll send it a 1 if you don't want to activate it. The FL pin here is for flashing. One of its functions is to flash the digits. And basically the important ones here are right here, A0 through A2. Those are the 3 pins we're going to use to address each digit in the display. And then because I think we'll be leaving A3, A4 high. Now we're cascading the displays here, so now the clock select and the clock in out pins become important. Because this is what controls our slave. Basically, I'll have one display as the master and the second display as a slave. We'll get into that into the schematic here momentarily. The right pin, same way, active low. Chip enable, very important when we're cascading displays, because I've wired up separate pins for each display on the microcontroller. And depending on which pin you activate, enable, and pull low, we'll pull one pin low, depending on which display we want to write to, and the other pin will be the other CE pin on the other display will be high, or vice versa, just depending on which display we want to write to. Positive supply VCC. We're pulling 5 volts off of the. We'll be pulling it off the USB to serial converter. Same one we used in the last lesson. So far it seems to be working okay. You always have to worry about pulling too much I think it was 500 milliamps on the USB protocol, but I was testing out. So far it's working alright, it's not complaining. Supply grounds, no problems, and pin 17, there's no connection there. So it's kind of weird. I put mine in the breadboard and try to line pin number 1 with the top hole in my breadboard, and then once I can get once I get one pin in for each one of these sets, then you kind of get your bearings as to wiring the other pins, just in relation to, because remember there's only six pins in the first set, 6 in the second, with a gap in between. These are these no pins sections. You have another ground for the logic, so you just put that to your regular ground. Read pin will be holding high all the time, we're not going to use. And then you have your data bus, the same as on the other chip, D0 through D7. And you can see your cascading displays. It's designed to drive up to 16 other displays. General requirements for cascading: you need to determine the correct address for each display. Use the CE. They're saying from a decoder. We're just going to use 2 pins from the microcontroller, one for each display, and whichever display we're using, we'll pull that pin low and leave the other pin, makes the other pins high. And unless we want the data to go to both displays. And then clock select. Your clock select pin needs to go to VCC, and then that's for the master display, and then the clock select will be grounded on the other display, and you can use reset to synchronize the blinking so they blink together at the same rate. Small diagram. I'll go over a schematic here in a second, but basically you wire one for one your data bus, your D0 through D7. You'll run them, the D0 on one chip to the D0 on the other chip, the D1 pin to the D1 pin on the other chip, etc., all the way up to D7. And then you'll have your read, your write, your FL, your flash, your reset, and your 2 clocks. Correction, up to reset, those will all be wired together. So read on one chip to read on the other chip, write on one chip to write on the other, FL the same, reset the same, and obviously our clock input output and clock select will be wired different depending on which chip it is. Alright, so here's the wiring diagram showing how the 2 displays are hooked up. Like I said, basically D0 will go to D0 on the other pin. Excuse me, I gotta pick whatever display you want as your master and your slave, and then stick to it so you don't get confused. But the bus will be connected one for one together. Reset, one for one. Your read write, same, and your read. Obviously your VCCs will just go to your power, your grounds to the ground. And then the difference being your clock select on your master display. The one that's connected to your microcontroller, that'll be your master display. That clock select pin will go to VCC. And then your clock select pin on your slave, the one not connected to your microcontroller, will go to ground. Then you have your CE chip enable pins, and one obviously your master will go. We'll pick a pin on the microcontroller to be our master enable pin, and then we'll pick another pin on our microcontroller to be the slave enable pin. Then when we write our functions, we'll include these, depending on whether they're writing to the master or the slave. Alright, so your master display, remember our slaves, like on their other diagram, is over here with all the connections going to that, like I just explained. And then your master display is going to be hooked up to your microcontroller. Your data bus, we'll have set up our port A as our data bus, and port A0. Correction, not our data bus. Our data bus is over here, and it's going to port C. So our data bus here, D0 to D7, going to port C. And then I wired up our port A for our reset FL and our addressing pins, A0 through A2, and then our clock select and clock input output, read write, chip enable. Basically like I said, the chips that are the pins that are important are the 2 chip enables and the clock select, clock input output, and basically I think most of the rest is what we've already dealt with. And of course we'll have our USB to serial converter hooked up just like before, and that'll be sending our byte over into the microcontroller, which will then send it, depending on which pin we have. I think I had a pin, I should have this wired, hold on. Alright, let me go into my program here. Alright, so I've got my chip enable master, my chip enable slave. Chip enable master to pin 1, chip enable slave to pin 0. So that's these, I had it on port B. So the pin 1 and pin 0, I didn't put it on the schematic here, but each one of these pins, pin 1 going to the master display, and then pin 0 going to the slave enable pin. And basically a very similar setup we had before. You just assign your pins how you want to put them in, to match your schematic, and then make sure your ports are assigned as outputs and not inputs. And you can see I've written a whole bunch of functions here, basically for each digit in each chip. So this would be like the master chip here, the 0 digit, the 1 digit, the 2 digit, the 3, etc. up to 7 for the master, and then I have it separated functions for the slave. And the basic is almost the same as last time. Here you notice I've got the 0, so I've got the chip enable master. We're sending data to the master in this function because I have a pull low, the chip enable pin pull low on them, and then the for the slave I have it high, so I'm writing data in this function to the master display. And then I'm pulling A3, A4 high. Don't need it right now. And then your important ones here, A0, A1 through A2. These are addressing, basically this is going to be for the 0 digit. And this will change as each digit you go to. These 3 little combinations will change. FL and read are high. Not using them right now. My data bus, just like the old IPD switch, and then I've got the read or the write. So I have it high, pull it low, bring it up high. I don't think I have to do all of that, but I at least have to pull it low, from high to low, and that's when it writes, I think, if I remember correctly. And then this is the same. Basically, you can just copy the whole function once again and just copy it and make another one. This is for the first digit, and only see the difference here. A0 through A2, I've got high, low, low instead of up here where it's all low. And that's the thing that's going to change. And obviously your chip enable will change based on what display you're running to. I'm running out of time. See you on the next one.